Okay, I think it's time for our second talk, and it's my pleasure to introduce one of my current co-authors, Jochen Glück from Passau, and he will talk about a topic which will also arise in the next talk by Sahiba, I guess. He will talk about eventual positivity, and he will talk about examples, results, and perspectives. So, Jochen, please enjoy your talk.
Thank you very much for the kind introduction, Christian. So yes, I'm going to talk about eventual positivity of operators in the groups, mainly about examples, maybe, let's see. So this is a 25-minute advertisement block for the theory of eventually positive semigroups. Let's start with an example to motivate why I want to discuss eventual positivity. So this is one example. So I want to discuss a version of the heat equation, but actually a biharmonic version of the heat equation. Let's say on an interval. So let's consider a operator, call it A. And let's say it's defined on L2 over the unit interval from 0 to 1. There's a domain D of A, maps into L2 again. And let this operator be given by, let's say, the following. So I want periodic boundary conditions, and I want a biharmonic operator. This means I want to consider the fourth derivative. The fourth derivative means I need a Sobolev space H4. So D of A is the space of all H, V in H4, with the property that the boundary values of V behave periodically, and the derivatives of V behave periodically. Okay. And consider the following evolution equation associated. Oh, sorry, maybe I should say how the operator acts actually. So AV is supposed to be defined as minus the fourth derivative. So minus V prime 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 prime. Or in other words, this is minus the Laplacian square of V. Okay, and we would like to study the heat equation, so the evolution equation associated with this operator. So consider the following equation. So we're looking for a function u and the temporal derivative of u. So u is a mapping from the positive from a line into the Banach space L2, and so the derivative, the temporal derivative, is supposed to be A times u, so the standard Cauchy problem for this operator A, and we have an initial condition u0 is some function in L2 over the unit interval. Okay, now why is this interesting? It's interesting because it's a fourth order problem here. Sorry, I always got the wrong color. It's a fourth order problem, as you can see here. And for fourth order problems, we do not have typically positivity preserving properties. Yeah. So let's write it down. Fourth order problem. Fourth order problem implies no positivity preserving. Yes, Delio has a question. Sorry, Delio, I can't hear anything.
We can't hear you, Delio.
Can you hear me now?
Yes.
Yes.
Okay. This is a fourth order operator. So aren't two boundary conditions missing?
And we have four boundary conditions. Yeah, I'm sorry, just a second. You're right, actually. Oh, yes, thank you. So good point. I should add a few more here. Let's do this. Good point, thank you. So if I have just a second, yes, I should add. Yeah, I need 4 equations actually. So sorry, that's embarrassing, quite embarrassing. Let's change this here. This happens when you only think about, oh, it's periodic, it's fine, and don't think about the details of the implementation of the operator. So I want all derivatives here to be periodic up to the third order, not up to the first order derivative, but up to the third order derivative, right? So I want here for all k from 0 to 3. Thank you very much, Delio. Okay, now, anyway, it's a fourth order problem indeed. Now with good boundary conditions, so that it really generates a semi-group. And we do not have positivity preserving properties here. And this is due to the fact, well, there are various ways to see this. There are general results which actually show that the semi-group generated by fourth order operators cannot be positivity preserving. Here you can also see it easier because you can simply write down bilinear form, which is associated to the operator, and then use the Berling-Unique criterion to show that it is not positive. So no positivity preserving property. Anyway, we have a weaker form of positivity here, and I'm going to show you this. So of course, the solution to our Cauchy problem here is of course that u of t is simply the zero semi-group generated by A times the initial value u0 for all t. Okay, and for this
to be in time, so maybe let us start with this session.
I want to show a weakened form of positivity preserving property. Now, how am I going to do this? So no positivity. However, since we have periodic boundary conditions here, it's not difficult to see that 0 is an eigenvalue of A, and the corresponding eigenfunction is just the constant 1 function. Yeah? So, and it's also not so difficult to see that 0 is the leading eigenvalue of A. For instance, you can show just show a dissociativity estimate for A or for the associated form. So 0 is the leading eigenvalue of A with eigenvector 1. Okay, now this implies if I start with a value u0 in L2 and apply the semi-group, then, well, it has compact resolvent, this operator here. Since you're on a bounded interval, it's a differential operator, compact resolvent. So this means it's self-adjoint too, that we can do a eigenfunction expansion of the semi-group. And if we do this, then we see that all the higher modes fade out as time comes to infinity. Only the 0 eigenvalue, the leading eigenvalue, stays here. And then we see that this converges to the eigenfunction 1 tested against the initial value times the eigenfunction 1. Yeah. So this here is simply the integral of u0 or the interval times the 1 function. Okay. Now that's interesting because if u0 is positive, this means that this is positive, so at least the limit is positive, right? But I want to show more. I want to have more than the positivity of the limit. I want to have positivity of the semi-group for large times. That's why I called the talk eventual positivity. Now, why is this true? Doesn't really follow from this convergence for t to infinity. Well, it follows if we make one more observation. So observe the following. A is self-adjoint, which implies that A is the semi-group is analytic. Yeah. So since the semi-group is analytic, in particular, all the semi-group operators map the entire state space L2 into the domain, right? So for all non-zero t, e to the ta L2 is mapped into d of A. Now d of A is actually a subset of H4 with 4 boundary conditions actually, and H4 is a subset of L infinity in 1 dimension. So this means e to the ta maps L2 into L infinity for every non-zero t. Now it's automatically true that this mapping has to be continuous from L2 to L infinity. You can try to explicitly prove this, or you can just say I'm lazy, I use absolute nonsense. So I am lazy. My abstract nonsense argument is a closed graph theorem. Yeah, it's continuous from L2 to L2, and it maps into L infinity. So it's also continuous from L2 into L infinity. Okay. So let's say E at the time 1 times A is continuous from L2 to L infinity. Why is this useful? But it implies, if I start once again, now I do the same computation as above here. So the violet computation, I do it once again, but I split off an semigroup operator at time 1. And I say, okay, so this is e to the time 1, e to the t minus 1a u naught. Now, this part here, which I've underlined now, converges again to the integral times 1. So integral times 1 function, right? And 1 is in the kernel of the generator, so it's a fixed vector of the semigroup, which implies that the semigroup operator times 1 is simply 1. So I say, okay, this is the integral times 1 for t to infinity. Okay, now what's the benefit of this little computation? Well, this convergence of this to this is an L2, but this operator, which I marked now, e to the 1 times a, is continuous from L2 to L infinity, which means that the convergence actually takes place in L infinity. So with this here, let's mark it in blue because it's important. This is in L infinity. Okay. So what can we conclude from this? This here converges to this in L infinity norm. Now, if we assume that u naught is positive and non-zero, then this number here is strictly positive. And so we have convergence to a strictly positive multiple of the 1 function in L infinity. So this implies that this here has to be positive for t large. And thus we have shown that the semigroup is, despite not being positive, it's eventually positive. Yeah. So this means, so there is t naught larger than 0, such that e to the ta u naught is positive for all t larger than t naught. Okay. Now this is a bit sloppy actually, because in this last line which I've written, I have not told you what's actually up with u naught, right? And the important point is here, if I say there exists t naught, well, does this t naught depend on u naught or does it not depend on u naught? The argument which I've shown you now just shows that for each u naught, there exists t naught. And for each initial value, we find the time from which on is positive. This is what I call individually eventually positive, and because it's an individual time for each initial value. But in fact, even more is true. In fact, we have uniform eventual positivity. Oops, that's one I too much. Sorry, what is that? My apologies. Positivity. No, I think it's correct. Uniform eventual positivity, and uniform means t naught can be chosen to be independent of u naught. Independent of u naught. And why is this true? Well, here's a theorem. So this is 2. Theorem. So let's consider a finite measure space.
It is time.
Finite measure space. So let A be a self-adjoint generator. Self-adjoint generator of a C0 semigroup on L2 and assume two things. So the first thing I assume is, as before I had that the semigroup maps into L infinity. Well, let's assume the same thing for the moment now. E to the TA L2 maps into L infinity. And I assume that, well, A has a leading eigenvalue. Actually, it has a leading eigenvalue because the condition which I just broke down automatically implies that A has complex resolvent. So it has eigenvalues, and assume that for the leading eigenvalue lambda naught of A, we have that the corresponding eigenfunction is spanned by the constant one function. Spanned by the constant one function. Yeah, so this way. So this is true. So this is the same situation that we had above, but more general. It's not related to the concrete operator. Then actually, oh, and maybe I should say what T is in this line here, right? Mention what T is. Let's say for some T. For some T. Okay. Then there exists a time T naught such that for all larger T's, we have that the operator is positive. And by positivity of the operator here, I mean that it maps positive functions to positive functions. So this is uniform eventual positivity. One can prove this in a general setting and then apply it to the example. Now I could say many more things, but I don't have too much time. Just two remarks. The first is we do not really need the one function here. And we do not really need L infinity. Here we can generalize this. If you have another positive first eigenfunction, so positive means positive almost everywhere, and I replace L infinity by an appropriate space related to the eigenfunction, then the same still works. I just chose it to write it down in this setting because it's simpler to state. Okay. And the second thing is, well, why is this true? One can prove it by a duality argument. And if one has a look at this duality argument, then we can see that it's even true in a more general setting than for self-adjoint operator. One can also write it down for non-self-adjoint operators. It's just more complicated to write it down. Okay, so this is, let's just write proof duality argument. It's not completely trivial, but one can do it. Duality argument. Okay, now, great. So I have 8 more minutes left, and I want to show you another thing. Examples. Examples are always good, right? So example 3, and I always wrote. Somehow I'm always pressing the wrong button.
Yeah, I think you can start.
3 example. One more example. Okay, I showed you the biharmonic heat equation in the interval of periodic boundary conditions. Now let's have a look at the biharmonic heat equation with on the whole space. Yeah. So for instance, consider now on L2 of the space RD, so no boundary conditions. D of A should be just H4. And the operator should now be minus
from the department of place.
Yeah, so maybe let's write it like this here. Okay, so you can also, this indeed is a self-adjoint operator.
Our next speaker is Delio Muniola.
And one can ask for eventual positivity, just as in the case before.
Here,
now this is a bit different because this operator does not have eigenfunctions or eigenvalues. It is just continuous.
Let me see the title.
So it doesn't work this way. But nevertheless,
Delio, what was? Can you show me the first page so that I will not?
Eigenvalues.
Yes.
So
it is on the Einstein-Riebeck operator on matrix diagrams.
Probably a bit too much to ask. That one has.
And our next speaker
eventual positivity.
is Delio Muniola.
That one has a local version of eventual positivity.
And our next speaker is Delio Muniola.
Positive U naught. No? Positive U naught. And now it's also interesting because we do not only need L2 but also L1. So in L2 intersected L1 of the space. And for each compact subset, so a local result now, compact K in RD, there exists a time T0 which now depends on U0 and on K and so on, such that for all larger times, e to the TA U0 restricted to K is positive, and no, I should not write for all T larger than 0, it's eventually positive, so for all T larger than T0. Okay, so this is local eventual positivity.
And our next speaker is Delio Mugnolo.
Local version thereof. And why is this true? Well, there are two ways to see this. The first way is one can prove it by kernel estimates. Kernel estimates. This was done in 2008 by, I think, by Ferrero and Gasola. Hope I spelled the name correctly. And also Grunau. So I'm not too good with names. Okay, Grunau. And one can also do it by alternatively by Fourier transform methods. Yeah. So instead of using explicit kernel estimates, Fourier transform methods. And this was done last year by Daniel Danners and myself and Jonathan Bui in Sydney. And the advantage of the Fourier transform methods is actually that they allow more generalizations. So one can generalize the results from the whole space to infinite cylinders, and that stays true. So let's say can be adapted for generalizations. Can be adapted for generalizations. Okay. So here we have local eventual positivity. And now this is interesting because local eventual positivity can also be treated in a rather general setting. So there's quite a general paper on it by Sahiba Arora from last year. I think it's going to appear in Journal of Operator Theory. So Arora, well, 2000, I think it was accepted in 2021. Okay, so this is a general paper on local eventual positivity, but again, it cannot be applied in this specific setting here because it also needs eigenfunctions. Yeah, so as in the result above, which I showed you here, 0 and 2, the paper by Sahiba needs eigenfunctions, but it has a treatment of those local properties in a very, very general setting. So what remains open is to find an abstract explanation of this behavior on operators on the whole space which do not have eigenvalues. Yeah. So we understand eventual positivity and local eventual positivity on bounded domains in a certain sense. But we do not fully understand it in an abstract sense on the whole space because we cannot employ eigenvalues. That's my last remark. For open problem. So find a general theory to treat local eventual positivity for operators, and if you like, add self-adjoint here. Yeah, self-adjoint would be okay for now. For operators which do not have leading eigenvalues. So that's an open problem. We have some ideas, but we're not sure whether they work, and it doesn't seem to be easy. So consider it a challenge. All right, it's good to end on an open problem. Thank you very much to everybody for listening.